In today's video, I have brought you a very nice problem regarding functional equation. Here is the following application. We have from z to z as integer numbers. So we have this composite function. We have f of x plus y equals f of x minus f of y. Okay. So the question, we are going to find all functions f. Okay. Always before we get into the proof, always you are going to check the smallest values of x and y. Okay, so because it's very important to reduce the expression to the smallest expression possible in order to proceed with solution. Okay, first of all, I'm going to take x equals y equals 0. Okay, let's set x equals y equals 0. Okay, so this one is going to give us f of 0, which equals f of 0 minus f of 0, which equals 0. Okay, so we get here f of 0 equals 0. Okay, this is more helpful. Okay, so our goal, we are going to find f of 0 first. How to get to this one? Let's set f of 0 equals a. Okay, we are going to find a. I'm going to apply f on both sides here, so I get here f of a equals f of 0. Okay, I'm going to replace x with a and y with 0. So let's set x equals a, y equals 0. Let's replace these two values into the original equation to see what's given us. So I get f of a, y will be replaced with 0. I get equals f of a minus f of 0. Okay, now let's replace here f of a with this one, f of 0. Okay, so I get f of 0. F of a will be replaced with f of 0 minus f of 0. Okay, so if you take a look inside of this one, f of 0 equals 0. Okay, then also f of 0 equals 0, which means I get f of 0, which is this one here, equals 0 minus f of 0. Okay, let's take this minus f of 0 to the left, and I will have 2 times f of 0 equals 0. Thus f of 0 equals 0. Okay, now let's move on to calculate f of 1. Okay, so let's set f of 1 equals b. So we are going to find b. Okay, let's replace x with 1 and y with 0. Okay, so let's set x equals 1, y equals 0. So I will have the following expression. I get f of 1, which equals f of 1 minus f of 0. Okay, we already know f of 0 equals 0. Okay, also we know f of 1 equals b. Okay, so we get here f of b equals b. Okay, now let's save this one for later, and then also I'm going to put the inverse here. I'm going to put x equals 0, y equals 1. So let's set x equals 0 and y equals 1, and take these two values and insert them back into the original expression. I will have f of 1, I will have the same thing here, which equals f of 0 minus f of 1. Okay, we know f of 0 equals 0 because we already determined that it was 0. Also f of 1 will be replaced with b. Okay, and also this one equals b. F of 1 equals b. So I will have the following. I will have f of b equals minus b, like this. Okay, here also we have 2 things here. We have f of b equals b, f of b equals minus b. This one implies b equals minus b. In the other words, 2b equals 0 because I'm taking minus b to the left. So finally b equals 0. So I found b equals 0. Thus f of 1 equals 0. Okay. And I found two things. So I found f of 0 equals 0 and f of 1 equals 0. Okay. Let's get rid of this one. Now let's get rid of this one and move on to the next step. So previously we were working on small values f of 0 and f of 1. We found f of 0 equals 0 and f of 1 equals 0. Now let's move on to work on general case. Okay. I'm going to replace y with 0 and leave x free. Okay. Let's set y equals 0. So I will have the following: f of x equals f of x minus f of 0. Okay. We already know f of 0 equals 0. Okay. Now let's set x equals c as an integer. Okay. As an integer number, and y equals 1. Okay. Let's take these values back into this one. So I get here f of c plus number 1, which equals f of c minus f of 1. Okay, like this. So I get the following: I get f of c plus number 1. So I'm simply replacing x with c plus number 1 into the original equation, which contain x. Okay. So which equals f of c plus number 1 minus f of 0, which is 0. We get the first equation is the same as the second equation. So I'm going to put this one equals to this one. So I get here f of c plus number 1 minus f of 0, which equals f of c minus f of 1. Okay. Let's consider this one is true for x. For all x as an integer, so we get f of x plus number 1 minus f of 0, which equals f of x minus f of 1. Okay. Let's put x term on one side and constant to the other side. So I get the following: I get f of x plus number 1 minus f of x equals minus f of 1 minus f of 0. Okay. We know the difference of these two functions is given as a constant. This one is a rare way telling us the function is a linear function. This one is not just equals to a constant, but also equals to 0, because we already found f of 1 equals 0, also f of 0 equals 0, which the whole thing equals 0. Of course, is a constant. Okay. So by taking this f of x to the right, I get the following: I get f of x plus number 1 equals f of x. Okay. We have ended with this nice expression for all x as an integer. Okay. Let's express this one inductively. For all n as an integer, we have f of 1 equals f of 2 equals f of 3, and all the way down equals f of n minus 1 equals f of n, finally equals f of n plus number 1. Okay. When we see like this, we are increasing the values of n. Okay. But the output of these values equals the same thing. Okay. The function is not growing. Okay. It stays the same. Which means the f of equals constant also. Okay. Thus f of x equals c. Okay. Where is a c is a some integer like this. Now the only thing we need now, we need to determine the constant c. Now it's more simple to determine the constant c, just replacing x with 0. So we get here f of 0 equals c, which equals 0, because we determined f of 0 equals 0. So finally f of x must equal 0 for all x as an integer. Okay. So we have determined the function f of x equals 0 for all x, the integer numbers. So one more thing I can add here. So by the definition, since we know this one is a linear function because we have this difference f of x plus number 1 minus f of x equals constant, which means the function is going to be written on the form of the linear combination, okay? Which means the function is continuous and differentiable, okay? And the limit exists, which means we have by the definition of the derivative function, so we know the limit of f of x plus h minus f of x over h, where is h is approaching to 0, which equals f prime of x. What this one is representing? Is represent the slope, okay? So if I'm going to express this one on this form, so I get the same thing here. So get x plus number 1, replacing h with number 1, okay? Here at this time, we're replacing h with number 1, not 0, which means h is going towards number 1. Equals slope. Since we get this slope, since we get this is difference equals 0, so which means this one is 0. So what we know that if we get f of prime of x equals 0, which means the slope equals 0. So which means the slope is going to, if the function is going like this, so we get the slope alpha, for example. So but so if you have this function is going to be written on this form, ax plus b. But in our example, since we get the slope equals 0, which means this alpha equals 0. So which means we have a parallel function here. So which means our function is this one. So you keep changing the value of x, but the output of these points stays 0 here, okay? We have the line, which means the alpha equals 0, which means tangent of alpha is 0. We get the 0 here, okay? I have ended this video. By the way, don't forget to hit the subscribe button and support the channel. And thank you for watching. I will see you next video. Bye.